Thank you very much for having me here. Let me try to share my screen. Okay. So let me start by thanking the introduction, and also thank you for inviting me here. So last time I was at the Black Hole Initiative was a few years ago. It was very nice. First to be back at Boston virtually. So now today I want to talk about I sort of think of wider interest than just in mathematics. And this problem is the starting point is to try to think about high frequency limits or just high frequency waves in general relativity. And there's a particular mathematical conjecture that I want to discuss. Is one that was proposed by Burnett. So here's the plan of the talk. So I'll start by the general background, sort of telling you what's the problem I want to talk about, what's high frequency limits. And then I'll tell you what the Burnett conjecture is and what we can say about the conjecture. And by that time you would complain that, okay, how can this guy come to the Black Hole Initiative and not say anything about black hole? And then I'll go to talk about how this relates to something in black hole, and then I'll finish the talk. Okay, so that's the plan. So let's think about what high frequency limits are. So high frequency waves, of course, have been studied very, very long time ago. So in a very important landmark paper, in fact, two papers by Richard Isaacson. So he studied what he called gravitational radiation in the limit of high frequency. Okay, so these are two sort of back-to-back papers in the physical review. And the setup that he wants to understand is the following. So what he wants to understand is he wants to do a kind of perturbation theory, which is very high frequency. So you want to look at gamma here that I have, which is what you want to perturb around. And you want to perturb with something small, but not just something small in the usual sense. It's something small, but very, very high frequency. Okay. So what he did is he quantified this with a parameter lambda. You should think lambda is a positive, parameter that would go to 0. And so this is small, okay? So lambda is small. So this is a perturbation with a small amplitude. However, it's highly oscillating. So the perturbation h also depends on lambda in a way that, okay, if you look at h itself, it's order 1. So the perturbation lambda h is of size lambda, so it's small. However, if you differentiate h, then it's large, okay? So it's large in terms of 1 over lambda. And if you differentiate twice, okay, there shouldn't be another comma here, it will be lambda to -2. So it has amplitude lambda, but also a frequency 1 over lambda. Okay, so this is the setup that he wants to understand. So one of the phenomena that he already observed in this paper, in particular in the second paper for which he thinks about the nonlinear terms, is that now suppose you want to think of the Einstein's vacuum equation. That is to say, you want to set G to be a vacuum. The Ricci curvature is 0 for every lambda, positive. Okay. Now you try to understand the limit, then you realize that the limit gamma doesn't have to be vacuum. In fact, it can have. You compute the Einstein tensor, you look at Ricci minus 1/2 of R of gamma, then this thing is not 0. So you can think of this as an effective stress energy momentum tensor arising from high frequency waves. Okay? So let's look at, so there are many, many works since the work of Isaacson. I list just a few here, some of which I'll talk about in more detail in the talk. Okay. So in order to have something to think about, let's look at a particular example of how this can happen. So this example was actually given explicitly by Burnett in 1989, and this is within a class of a plane wave metric. Okay, so I want to understand how this can happen, how I can have some high frequency perturbations so that I create an effective stress energy momentum tensor or matter field in the limit. Okay, so everything is explicit, so let's write this down. So what Burnett considered is the plane wave matrix. So you can consider the metric, which is of the following form. Okay? So you look at G on a manifold, and this has coordinates U, V, Y, and Z. Okay, so this is okay. So just notice that if you set H to be identically equal to 1, so that let's say this is equal to 1. And G is equal to 0, and therefore this would be equal to 1, and this would also be equal to 1. This is nothing but Minkowski, okay? So this is Minkowski in a different coordinate. So now what you see is that plane wave metric is just a generalization of Minkowski metric. In general, it does not have to solve the Einstein's equation. So if you try to look at this metric, and if you compute the Ricci tensor, it does not have to be 0. But nonetheless, you can check that essentially most of the components of the Ricci curvature tensor is 0, except for one, which I have written down here, which is the VV component, and it has an explicit form that you can write down in terms of the functions exchange. Okay. So now, well, once you know this, now you can say, well, now you have a way to generate a lot of vacuum solutions. Okay. So what you can do is the following. What you can do is you can prescribe G as you want. It doesn't matter. Okay. So now we all know that all Ricci components except for the VV component is 0. So I can just think of the equation here, this equation, Ricci VV equals to this, as an ODE. And I solve this ODE for H, and this I can get a vacuum solution. Okay, so there's a way to generate many vacuum solutions from this ansatz. Okay, so what did Burnett consider? So now what you want to do is you want to consider a one-parameter family of solutions to the Einstein's equation, like what we did in the example in the first slide in Isaacson's paper. So what you can do is, okay, I can set everything in my one parameter family to be plane waves. Okay, so I write this down. So it depends on a parameter lambda. And for every lambda, I have to tell you what G lambda and H lambda are. Okay, so the way that one can choose the G lambda is, well, I set it to be this particular form, which is, this is lambda times just a smooth non-zero function times a highly oscillatory phase. Let's say sine v over lambda. Okay, so notice that this is exactly the kind of thing that you see in Isaacson's paper, because G is small, it's of size lambda. If you take the derivative, it's of size 1. If you take, the second derivative, then it will be large. Okay, so this is a very highly oscillatory thing. And I want to say for every lambda, I want to have something that's vacuum. So suppose you give me, I write down G like this, I can solve H by the ODE, right? So remember, this is the ODE that I want to solve so as to get vacuum. And I just write down what G exactly is. So I solve this. So for every lambda, I have a solution to vacuum. So now let's try to understand the limit. Okay. So obviously the limit of G would be 0 because lambda goes to 0. This right-hand side here goes to 0, right? So then the limit will be 0. But what about the limit of H? Okay. So now let's try to understand H. H, of course, is satisfies an ODE. And I can try to take the limit, but notice now if you look at the right-hand side of this ODE here, well, as lambda goes to 0, the amplitude does not go to 0 anymore because I've taken the derivative of G. Okay, so this is something of size 1 and highly oscillatory. So in the limit, if you want to integrate the ODE, what this looks like is that cosine squared would essentially look like 1/2 plus something very oscillatory, which when you integrate the ODE, you integrate out. So at the limit, what you would get is you get H naught, say the limit of H, will satisfy the ODE, which is 1/4 of k squared, which is not 0. Okay, and 0 would be what corresponds to G prime squared because the limit of G is 0. So now what you see is that at the limit, this is no longer vacuum. So now this is example. Compute everything. Now you notice that this limit that I've written down here, now G is already gone because G naught is just 0, so e to the G naught is 1. So I have this solution, and now you can say, well, this is actually non-vacuum, even though you start with something vacuum. And now you can try to compute what the Ricci tensor is. Well, it turns out that, well, not only is non-zero, it has a very specific form, and in fact, it emits a physical interpretation. Now you can write down this. In the limit, the Ricci curvature is some amplitude, let's say 1/4 k squared, and it only has the dV/dB component. And moreover, the amplitude has the property, well, that it only depends on V. Another way to say this is that you can think of V in your metric is now null hypersurfaces. So these are constant V null hypersurfaces, constant V. And what happens is that, well, you have this matter given by this, and this matter is just transport. It only depends on V, so you can think of it as just transported along constant V null hypersurfaces. And this is nothing but the Einstein now dust system, where you have the dust density is 1/4 k squared, and it's just transported in a light-like direction. Okay. So now that we know that this phenomenon can happen, now the natural question that one can ask is what can happen? Can I describe all possible limits? What in general can happen? So sorry, is there a question? I saw, is it a...
Yeah. Is this peculiar to the Einstein equation, or can you do things just like this with just a scalar wave equation or something?
Oh, that's an excellent question. If you allow me, can I come back to it in, I don't know, 10 minutes or so?
Okay, all right.
Yeah, but this is something you can ask more generally about PDEs, whether you have a limit of so you have a limit of solution is still a solution. Yeah, yeah.
Is also the possibility of your solution not having any limit also yet another?
Right, so this is also an excellent question. So it turns out what you can say sort of on very general grounds, which is suppose you have perturbations which is sort of this type of form. You have a particular first derivative, second derivative. What you can always say is that you can take a sequence of lambda marching to 0 so that there is a limit. It doesn't have to be unique. You can take different sequences to have different, but this is sort of general mathematical result which tells you that that there must be some limit. Okay. That's a great question. Okay, so right. So I want to understand what can happen in general, and this is where Burnett came in. So in this paper of Burnett, a little bit maybe 20 years or so later than Isaacson's paper, but still a long time ago. Well, he actually made precise conjecture of what can happen. Okay, so here are the conjectures rephrased in maybe slightly different language. Suppose you consider any high frequency limit in the sense of Isaacson on the first section, then well the limit must be isometric to a solution to Einstein massless Vlasov system. Okay, so you would have a limit. The limit actually solves an equation if you put in appropriate massless Vlasov field. So in particular, you should think that dust is a particular example where this is a Vlasov field which only moves in one direction, but in general it can move in many directions. So that's what he conjectured to be. And moreover, he gave another conjecture which says that well, this is really everything. Okay, so that is to say, not only every limit has would be you can identify with the solution to Einstein Vlasov, and in fact, any solution to Einstein massless Vlasov, you can achieve it as a high frequency limit of vacuum solutions. So these are the original words of Burnett. He said that well, given any tensor field obtained from this limit, one parameter family, then you must be able to find a scalar field A squared. So there's something positive on the null cotangent bundle, so that the stress and energy momentum tensor would be given by the integral of this in the appropriate direction. So this is exactly the Vlasov field, and moreover, the A is just transported. Okay, and for the second conjecture, he didn't exactly formulate it as a conjecture, but he said it would also be interesting to know if the converse of the above conjecture is true. If you give me any metric and a scalar field so that it satisfies the Vlasov equation, then there exists a one-parameter family of metrics satisfying condition 1 to 4, in particular their vacuum. If this is true, then we don't have to impose any restrictions on what fields A and G we use. So this is very general. So just let me say again, if the integral is a finite sum, then it reduces to the Navier equation. Okay, so in particular, it's consistent with the explicit example that we have seen. Okay. So Burnett himself gave a physical interpretation of if this is true, what this would mean. He said you can think of A squared, well, the Vlasov field as a particle distribution on the null cotangent bundle. If the conjecture is true, then we see that particles do not interact directly, but they do affect one another by the effect on the background spacetimes. So the high frequency waves, at the limit, they only interact through the background geometry. Moreover, you can completely describe how high frequency waves at the limit behave further. As he said, we then have a complete system for describing the effect of high frequency waves on background spacetime. That is, on a fixed smooth manifold, we have a metric. And on the null cotangent bundle constructed from M, we have a scalar field A squared. This field would then satisfy the Einstein-Vlasov equation. Okay, so what's known about this conjecture? So there's something that Burnett already proved, but I'm unable to get to the next slide. Okay. What you can say is, well, if it were true that the limiting stress energy momentum tensor, the limiting matter field, is Einstein-Vlasov, then there are certain properties that must hold true. And Burnett noticed that one of that he can prove, which is that it has to be trace-free. Okay, so this is in particular true for masses-Vlasov. A little bit later, more recently, Green and Wald proved that, well, in fact, the limit must also satisfy the weak energy condition. That is to say, if you contract T with two of the same causal factor, then it's not negative. Okay. So notice that if Burnett's conjecture were true, then in particular it implies the theorem of Greenwald, but the other way direction is not true. So for instance, Burnett's conjecture implies that T is positive. That is to say, Txx is not negative for any x, not necessarily causal. And moreover, you have a slightly stronger energy condition, which is true. Okay. So that's the theorem of Greenwald. But now we want to return to ask, well, can we actually try to prove the original conjecture of Burnett? Can we actually try to say that, well, all limit must be given by Vlasov, and conversely, all solutions Vlasov must be approximated by that? So as stated, that is still an open problem, but here's some of the progress that I've made with my collaborator Cécile Unul from École Polytechnique. So what we are able to say is we can't prove the result in the completely general case, but what we can say is suppose you assume a U1 symmetry in your spacetime. Okay, so a priori assume all the vacuum spacetime and also the limit, they are all U1 symmetric. You have a translation symmetry. Okay. Then what we are able to say, well, first there's the resolution of what Burnett actually conjecture is, well, we need the slight gauge condition assumption, but under this, a symmetry assumption, gauge assumption, what we can say is any high frequency limit must be isometric to a solution to masses-Vlasov system. So you can find a masses-Vlasov field so that you can identify the limit with a solution to Einstein masses-Vlasov. Well, the other direction, which is the direction that Burnett didn't explicitly conjecture, but they speculate, turns out to be harder, despite we worked on it first. So that's, we can say less. We can't say that any solution for Einstein masses-Vlasov must arise as a limit, but at least for a large class, we're able to construct something that approaches the limit, okay? So more precisely, the statement that we're able to say is the following. So suppose you give me some generic, small data, smooth, polarized U1 symmetric spacetime, which solves the Einstein null dust system. So this is just null dust. So it's a particular case where the integral is a sum with an arbitrary number, but just finite number family of dust. So you just have finitely many directions of dust, not a continuum of it. Then what we can say is then we can construct the sequence of vacuums solutions whose appropriate limit would be the given spacetime. Okay, so you can achieve it that way. Okay, so now let's try to think just in a very, very overview way why this is true and how I should think about this without going to the details of the proof. And hopefully we'll give an answer to Andrew's question. So I want to just briefly say why is this conjecture true? So it turns out the whole point to understand is try to understand how, on one hand, what's called weak limits, and on the other hand, how products, how they interact. Okay, so this is something about nonlinear PDEs that you can, in general, try to ask, because nonlinear PDEs typically involve products, and you want to ask how limits and products interact. So what do I mean? So here's what I mean by weak limits. So this is a notion easy to define. So I can think of limits. I can weaken the notion of limits and saying, well, just converging to a function by saying that well, a sequence of function converges to its limit weakly. If I integrate, pair it with a sufficiently nice function, then the integral converges for all sufficiently nice function. So in particular, this somehow smooths out all the oscillations and so on. Okay, so the limit you can have in mind is if you look at cosine, then of course there's no pointwise limit because it's just oscillate faster and faster, but weakly it converges to zero because all the oscillations are cancelled out. But the important thing about the weak limit is that if you have two sequences, one converges weakly to the limit, the other converges to the limit, the product does not converge weakly to the product of the limit. Okay, so limit and product do not commute, and it's very easy to see with a particular example. You look at sine times sine, cosine, where the limit is zero, but this is not equal to 0 plus 0 because okay, this is 1/2 plus an highly oscillatory part. Okay, so this is actually very similar to exactly what happens in the example of Burnett I gave you, which has to do with this type of oscillations canceling out. Okay, so now we can actually ask this for very general PDEs. So this is really a very general question that you can ask. And this already gives you a sense of what's happening in the particular case of Einstein's equation. So here it is. You can look at just, if you think of Einstein's equation as a wave equation, you can think, then you can say, well, why don't I just think of a wave equation, try to ask what happens. So look at, maybe you can think of simpler nonlinear wave equations, which is just the wave operator on phi equals to the derivative of phi squared, okay? So now what I want to do is I want to have a setup as before. I want to say, suppose I have a sequence of solutions. So there's all solutions, phi n. It converges to a limit. So there's a limit phi infinity. But the derivative only converge weakly. Okay, so in particular, it could be just sines and cosines oscillating faster and faster. Okay. So what can I say about the limit? So just because of the fact that the product of weak limit is not necessarily the weak limit of the product, you can easily build a sequence of solutions for which now the limit does not satisfy the equation anymore. You have an extra term coming from the non-commutativity of taking limit and taking product. Okay. But now here's what's amusing, is that in some other PDEs, you can somehow save this. And this is related to the Einstein's equation, because Einstein's equation is not just a general PDE, it's a very specific PDE which has a lot of structure. So here's the thing you can do. Consider you would think slightly different problem, which is to say, well, just change the nonlinearity a little bit. So this is well known actually. You just look at a sequence of solutions as before. Again, well, you know that the product of limit is not the limit of product, but nonetheless, the limit has to solve the equation in this case, because the nonlinearity is special. There's some cancellation that goes on. So this is well known in mathematics. It's a phenomenon known as compensated compactness. So this is a general thing you can ask for general nonlinear PDE, whether you have compensated compactness. So what happens for Einstein? It turns out that in Einstein's equation, something more amusing happens. So, well, the reason that we use U1 symmetry is that I can reduce it to Einstein wave map system into that 2+1 dimensions. And after choosing a gauge, let's say the equation looks like this, okay? So now I ask the same questions as before. For instance, I have a wave equation with nonlinearity. Can I try to pass the limit? Well, it turns out what we can say is that we can sort of pass the limit and not quite, but we can precisely describe the part that not quite. So we want to say, well, the limit actually satisfies the equation of this type. Okay, so the first equation you can pass the limit, the second you can't, but you create a new term which looks like a Fossil. What this tells you is that there is certainly some non-compactness going on because you can't pass the limit, but the non-compactness can be precisely prescribed, and this has to do with some hidden compensated compactness in the non-compact part. Okay, so this is what secretly happens. Okay, so that's all I want to tell you about the proof. But then now I want to tell you about a slightly different problem, and I want to tie this to maybe black holes. Okay. So here's a priori a completely different problem, which is first discussed in an even older paper of Singh. Okay. So what he did is the following. What he constructed is he constructed a solution to the Einstein's equation, which is quite amusing, which has now a dust shell. Okay. So let's draw the solution, not in the language of the time of Singh, but in sort of more modern Penrose diagram. So what you have is the following. So in fact, this is a black hole space-time. So this is the black hole. And what he managed to construct is just the following thing. So he has the solution. So this is a black hole. You have event horizon. This is Penrose diagram. What he can construct is that, well, he can find something which is Minkowski here. So this is just the flat space-time, and connect this to Schwarzschild. Okay. Of course, you can't just connect them. There's a problem when you connect them here. Okay. So things cannot be connected smoothly, and in fact, it cannot be connected in a way so that the junction satisfies the Einstein's vacuum equation. But you can think this is some matter field. Just compute what the Ricci tensor is, which is supported on a null hypersurface. Okay, so this is the delta function on a null hypersurface, and what you can think of is this is actually nothing but a shell of null dust. So this is like a null dust propagating, but it's a delta function, so it's just a shell of zero width. Okay, so this is the solution that Singh considered. Okay, so now this, just a second. So this type of solutions has sort of attracted lots of interest. So there are many different constructions of explicit examples. I list some of them here, but there are many more. So now this, okay, raises a question you can try to ask. Can you prove a general local existence theory for these Noether shell? Okay. So this really, at this point, I want to talk about the question which seems completely different from what I've been talking about. Okay. I just want to ask, well, can I have a local existence theory for Noether shell? Well, it turns out you can, and this is a result with Igor and Nyansky. And what we can show is the following. So what we can show is that you look at the initial value problem. Let's say you have initial data on two null hypersurfaces, and then you put a null shell here, put a null shell here, and now you can we want to ask if is there a solution, and what we can say is, well, there is a solution that you can construct, and you have two null shells and they can interact. Okay, so here's the theorem. There's a unique solution that has no two null shells. Now I bring to you the connection. Why do I talk about this when I'm talking about high frequency limits? Well, it turns out that the way we attack this problem is via the high frequency limit. Okay, so in other words, what we do is we know that, well, now dust is something that can arise in the limit of vacuum solutions. So what we want to do is, well, we want to solve for this Noether shell solution. Let's start with something vacuum and take the limit. Okay, so that's how we prove it. And in particular, what we can show also, just because of the way we tackle the problem, any Noether shell solution of the theorem would arise as a limit of smooth solutions of Einstein's vacuum equations in the way described above. Okay. So, well, let me just say maybe a couple of words. One thing is that this is very general local existence theorem without any symmetry assumptions. It goes through thinking about vacuum, and then I take the limit. But this is a slightly different phenomenon, if you want, than before, which is, well, before the example I've given you is that I have some matter coming out from oscillation. Thing oscillates very quickly. So this is one way that weak limits have problems with taking product. This is a slightly different thing that we try to exploit here, which is you can have concentration. Okay, and then what you have is you concentrate more and more, and then okay, eventually at the limit you get a shell of null dust. Okay, so now, well, this is all just about null dust, but now let's try to come back to black holes. Okay. So Singh's example, if you remember, it's not just an example of a local propagating null dust. In fact, it's an example of gravitational collapse, right? Because we have an example which is you have a dust. Well, you start with Minkowski, you have dust, and eventually you become Schwarzschild, and you actually have a black hole. So this is an example of gravitational collapse, which is one of the quite early ones that you can construct, and it's very simple to construct because everything is explicit. Well, you can try to ask, well, how general can I understand gravitational collapse? For instance, one question that has been quite difficult for a long time is, suppose you are only in vacuum. Can you try to understand gravitational collapse? Can you try to start with nice data and show that a trap surface or maybe even a black hole will form in evolution? Well, of course, now we know that even the vacuum problem is solved, right? So, which is much, much harder than the problem of Singh, right? This is a problem solved by Christodoulou about 12 years ago. What he showed is that, well, a trap surface can form dynamically in vacuum by the focusing of gravitational waves. So this is a much harder problem than Singh. In particular, okay, there's no way you can do anything explicit. And okay, many, many people since have worked on a related problem. But now I want to tell you that, in fact, there's another way to think about Christodoulou's construction, which is actually just Singh in disguise, if you want to think in terms of these limits. So here's one observation that you can make. So how did Christodoulou construct his solutions? So it's encapsulated in this picture. So what he did is the following. So he'd start with some place which is flat. Okay, so you should think this dotted line, this is Pascal infinity, square minus. And now at some point here, he sends in gravitational radiation inside, and then here you form a trap surface. Right? So that's the setup. So you have gravitational connect completely in vacuum, but the way that he constructed it, in order for the analysis to work, he requires something to be small in the problem, because PDEs are very difficult if you don't have anything small. And the thing that he has more, quite ingeniously, is a length scale. The data is large, but the length scale is small. So what he says is that, well, he can try to put gravitational wave in a very short length scale, and he can control the space-time all the way up to trap surface formation and describe this gravitational collapse. Well, now you can ask the following question, which suppose you have a small length scale delta. You can ask the question, what about if we take delta to 0? Okay. Well, it turns out this is exactly the type of limit that we were trying to take before. This type of limit is very weak, but you can nonetheless still take it. And this is the connection of Christodoulou and Sink, which is, in fact, if you take the delta to 0 limit, then the Christodoulou spacetime becomes a spacetime with the propagating null shell. There's matter in the limit, and in fact, it's something like Sink. Okay? So what's the lesson that we can learn from this? So one thing you can say is the following. Well, we now, of course, know Sink's construction. We know Christodoulou's solution. But suppose in a different world, we have never seen Christodoulou's construction. We don't know how to do that. That's a difficult problem. Well, there's one way to try to tackle this problem, which is, well, you can try to start with Sink's solution, which we know it's more or less explicit. We can know everything. But now we also know that, well, because it has no dust in it, you can try to approximate it with vacuum solutions. Okay. And in fact, okay, the vacuums, this approximating thing would be exactly what Christodoulou did construct. And you can then show that the approximating solutions actually exhibit the dynamical formation of trap surface and actually solve the problem of formation of trap surfaces in vacuum. This, of course, can be more general. You can suggest that, well, you can think of, if you allow language, Flassov field as a poor man's gravitational waves. So if there's a problem that's quite difficult to understand gravitational waves in general, you can try to study maybe Einstein masters Flassov or Einstein now dust to gain insight to the vacuum problem. So this is useful when, well, the problem with Flassov or with now dust is much simpler, for instance, when there's a lot of symmetry. It's useful when the phenomenon is dominated by high frequency waves, because well, this matter is about high frequency limits, and it can even provide insights on what the physics is, and also a mathematical way to think of the problem. And finally, let me just close with another story in black hole physics, which is I claim that the idea to try to think of Flassov field as poor man's gravitational wave is not new. In fact, this has been done in a very old paper. Well, not very old, perhaps, by Poisson and Israel. So this was one of the very first attempts to try to understand Cauchy horizons inside black holes. Of course, at the time, this problem was very difficult, but what they suggested is the following. So this is a direct quote from the paper. The problem becomes tractable if one first considers simple model. First, you consider a charged spherical Rice-Nordstrom black hole perturbed by cross-flowing radial streams of inflowing and outflowing outgoing light-like particles. This is very idealized, but there are good reasons to believe that it captures the essential physics. In the first place, the causal and horizon structure of Rice-Nordstrom and Kerr black holes are known to be very similar. But the second thing, what they mention is that the large blue shift of inflowing gravitational wave means the high frequency components will dominate near the Cauchy horizon, so that Isaacson's effective stress energy description for waves in effect the optical graviton approximation should be an adequate approximation. Okay. And of course, by now we understand that this is indeed the case. The physics near the Cauchy horizon of black holes indeed is captured by what a lot by what the Poisson and Israel did. For instance, in some of the more recent work that I have done with difference. Okay, so I think I already went a few minutes over time, so let me just finish the talk here. Thank you very much.
Yeah, thank you, Jonathan. Thank you for that very nice talk. We have time for questions. If you want to ask a question, you can raise your hand. Avi is first.
Yeah, so if we look more broadly, particles in quantum mechanics are waves, right? So you can think of the classical description as the high frequency limit of those wave packets. And, you know, the fact that we can describe general relativity classically, to me, implies that this must work. This program that you described must work. Would you agree with that?
So this I don't know. This is beyond what I know. So maybe prefer not to say anything. But let me just mention one thing. It's there is some relation in a very vague way. For instance, in sort of the proof of Burnett's conjecture, the tools that we use, actually we learned a lot from the tools that are often used to understand, for instance, semi-classical limits in quantum mechanics. The mathematics is quite related. Yeah, but but yeah, I don't know. Yeah,
Well,
that's a good point.
I mean, let me put it differently. If this program was not in effect, then how could we describe things classically with general relativity as a classical theory of gravity? I mean, it wouldn't be possible, right?
Yeah, it's a slightly different limit, but yeah.
Okay, I guess Martin wants to ask a question.
Hi. So Jonathan, thank you so much for a beautiful talk. Listened to two talks of yours in the last few days, so that's been wonderful. So I'm relatively familiar with Luk Rodniansky, both the 14 and 17, because Nikos and I used it and were very much thinking about it when we were doing our formation of trapped surface, right? That recently came out. And what I'd love to hear you kind of explain a little bit more is, so in Luk Rodniansky, you have uniform estimates on the region of existence. Now I'm guessing that's going to play a big role in what you're going to say, but I want to hear you kind of explain a little bit more. How does Luk Rodniansky actually, in terms of the estimates and the actual kind of details, how does it link with what you did here? And the second question is, well, actually, let's do that one first, and then okay. I'll wait for myself.
So let's try to go back to this slide. So this is sorry, this is okay. So about this this result. Okay. So right. So I guess maybe some prehistory to explain what Martin was asking, is that this result actually relates to a somewhat older result that Igor and I has thought about, which is a result which is completely about vacuum. Okay, and we use that heavily, as I just told you, that everything here we want to do with matter ultimately relies on understanding vacuum, and that actually helps us understand non-vacuum, right? As I pointed out, for instance, here. Okay, so now what one can say there. So what it turns out, maybe here I have more space to draw. In that old work, what we did is the following. What we did is that we can think about vacuum, but with rough data. Okay. So what does this mean? So suppose I have the characteristic initial value problem. What this means is I want to say if I have the metric, I only require, let's say if this is the U bar direction, this is the U direction. I only require the derivative of this to be in L2. Okay, so there's a squares integral. Okay, with maybe with more regularity in the direction that's in and out of the screen that I cannot draw. Okay, with let's call it angular regularity. Okay. So now here's the point. So now I want to understand limits of these things. Okay, so I want to look at a sequence of things which only obey this very weak estimate. So the first thing you can say is the following. Using our result, we can always say that you have region of existence, let's say here. Okay. And because, okay, you have region of existence, then you can try to ask if you can pass to a limit. So what's very interesting is the following. What's very interesting is a general sort of mathematical statement, which suppose you just know that you have a bounded sequence of function which are in L2. Okay. Then you can always have a subsequence which has a limit, but this limit has to be weak. Okay, so it's something like what I was saying would arise, because the limit is not strong. You can have non-commutativity of products and limits. Okay, so this is one. So the first thing we can say is that what you have the whole region that you can say from our old existence work, and you can always pass the limit, but the limit is weak. But now it turns out that okay, there are more estimates than just L2 that we proved. In particular, it depends on each component of the curvature and so on, as you perhaps understand very well. And some of the different estimates allow you to say for some components, you have some better convergence property. And this allows you to say that what limit must actually be null dust, okay? And this also allows you at the end to say that with any null dust, you can try to first approximate the data in vacuum, use our old vacuum result and try to pass the limit, and you get an evolution of your null dust data. So that sort of is the connection with the old work.
I see. So if I can understand very broadly with a broad brush that the renormalization scheme in, say, Luk-Rodniansky, which allows you to get rid of some of the bad components, but still you're able to close the system. So here I'm supposed to understand that. Okay, so that gives me the broad brush for this work. That's kind of what you just described.
Right. So I use that. You should say I already used that. I don't have to refer, in principle, I don't have to refer directly to every step of the proof from there. I just need to use the fact that using whatever renormalization we did, we can close the estimates, and there are some estimates for me now to use. And I just try to understand what with those estimates, what kind of limits that I can get. And that allows me to analyze the limiting spacetime. So
what were the main challenges? Like, what were the hardest bits, or what were the most challenging bits? What were the biggest difficulties?
So one of the things you can say is the following. So right, so it's the exact thing here. So you want to say, well, because things are only in L2, you worry that dg squared, right? So the limit, if you look at the sequence, the limit might not be the limit squared. Yeah? So this is a priori what you worry most, and this will happen because there's dust. But you have to check that most of the time it converges. Okay, so you need to use the structure. So now this really, the next sentence is really just for you. So for instance, if you just look at chi squared, then you know that the limit is not this does not converge to what you want. But then there's something more subtle, which is if you look at chi bar, then it does converge to the limit. It does converge to the limit. And this is something that has to do with some compensated components. Okay, but this is maybe too technical for this.
And is this highly reliant on some null structure miracle, or? Yeah,
it's related to that. Yeah, it's related to that. Yeah, it's related to a miracle. It's related to this type of miracles here.
I see. Yeah. Okay.
It's very related. Yeah.
All right, Jonathan. Thank you very much for a beautiful work and talk. Thank you.
Thank you for the question.
Okay, Alex has sent a question in the chat. He's asking, is the sink solution the same as the Vadya-metric?
So it's same as the Vadya?
Yes, so is the sink solution that you discussed with the null dust that collapses to a black hole the same as the Vadya-metric?
Yeah, it's maybe a most special case of it, right? If you want. This is a limiting case of it.
Yeah.
Thank you. I guess it's in the category of results not named after the people that discovered.
Sorry?
I guess it's another one of those results which is named after someone other than the discoverer.
But Vadya is more general, right? So I think sink was at least as far as sort of the limiting case is concerned. I think it was sink.
Okay, maybe I can ask a question as well. So, do you know? So there's something very similar that happens for calculations with near extremal black holes. So if the small parameter is just a deviation from extremality, various people in various calculations have noticed that there are certain types of calculations, including gravitational waves usually, where if you take the limit to the extremal black hole, if you take your lambda all the way to 0, you get all these persistent oscillations in actual observable fluxes near null infinity or down the horizon, which don't go away. It seems it's the opposite limit from what you have, because it's usually in that case it's the low frequency limit of waves which enter this near horizon region of the black hole. But it has a very similar behavior. This has been shown both analytically and numerically. Called the wiggles in numerics, and there are several analytic instances of that. In that case, the small parameter is just a deviation from extremality. But there, the limit does not exist for these quantities. So the oscillations persist all the way if you want to take the limit to extremality. Do you have any reason to believe that it's a related phenomenon?
So I don't know. Can I ask you something to understand that better? So is it already something that you can see at the linear level?
Yes, it's something you can see at the linear level. Yeah.
Yeah. So from that, I would think it's a different phenomenon. But okay, I don't know, because this is quite nonlinear. This is about I should maybe perhaps say that this type of thing, it's so if you look at this, if you look at the linear equation, then there would be no trouble at all passing to the limit. So this type of phenomenon really is is from the nonlinear term. But okay, but this is a naive answer. Whether there's a deeper connection, I don't know.
So Jonathan, I actually had two more questions that I just came to mind that I want to ask. So first is, could you talk about the uniqueness statement a little bit more? And second is, in the perspective of Anne Luk, is there a scale critical thing to be said here? Okay,
that both are excellent questions. So here, so presumably it's this uniqueness that you're asking about. Yeah. Okay, so that's a good point, because what I'm telling you is how we prove existence is exactly sort of what I try to describe, which is, okay, you have now dust data. Now I approximate it with vacuum data. I solve, and then I try to extract the limit. Of course, this sort of extracting limits, they don't have to be unique, as I already said sort of earlier. If you have general bounds, you can always try to extract the sequence for which you have limit, but they don't have to be unique. So that actually requires a different argument, not directly using our old work. And in fact, that's, if you want, it's most of the paper is trying to prove uniqueness. But while, okay, you cannot just sort of use our old work as a black box to prove uniqueness, it turns out that the proof uses much of the ideas from the old work. So a lot of the ideas can be used.
Could you give an example?
Well, well, for instance, the kinds of well, one thing that you have to understand in doing this sort of mathematics is you have to understand what function spaces you want to use. Right? For instance, renormalization and so on that you have already mentioned. So we have to do all that, for instance, and we have to do a little bit more because, okay, the dust is a measure, so okay, there's a little bit more to be done. But sort of the choice of function spaces is very much you can try to get inspiration from the old paper.
Okay.
The second question, right? Yeah. So here's also a very amusing thing, which is it's always interesting to try to understand whether you can have something more globally. So this is a good example that you mentioned, but so that again we're all not all lost. Let me try to explain what was in your question, which is what Martin was mentioning is some work I did with An. Maybe it's best to do it in this picture. So I have done some work with An, which does the following. So we want to try to understand Christodoulou picture better. In particular, can I have much weaker focusing and still get a trap surface? Okay, so what does that mean? So what Christodoulou did is he looked at this picture with the delta length, and he tried to set the shear to be of size delta minus a half. Okay, so you have a short length scale and you have a huge spike. Okay? And what I did with An, what we said is that this is much weaker. Let's say just a small constant. Okay, very small constant. Well, it can be even weaker. So now you can ask the following, try to understand the limit as delta goes to 0 in both cases, and what's the difference? And it turns out that if you look at this case, and if you take delta to 0, the limit is flat. There's no trap surface whatsoever. So there's some scaling that one has to think about in order to think about this. And why is this consistent? Why can we prove a trap surface that forms for every fixed delta, but at the limit, there's no trapped surface and gasoline fat. And the reason is, of course, that in our work, what we showed is that for smaller and smaller delta, you have to go further and further away to get trapped surface. So it's completely consistent that locally, everything converges to flat. So that's the picture. So sorry, I see something in the chat. Oh, okay.
I don't see anything more. But if anyone wants to ask any question, please unmute yourself and go ahead. Okay, I guess if not, we're at the hour, so we should thank Jonathan again for a very nice talk and very stimulating, and everyone for the questions. Thank you,
Thank you again for
Jonathan.
inviting me.
See you next week.